Welcome back. In this video, we're going to start up chapter 3, which is on math models. And you should know whenever we talk in a math class about models or modeling, we essentially mean word problems. And so the first part of this chapter, we'll go over just kind of the basics or strategy of how to attack word problems, and then we'll actually start doing it. As always, though, whenever we start a chapter, it's a good idea to look through the sections and see just what it is that we're getting into before we get into it. So the sections in this chapter, there are 6 sections. 3.1, as I mentioned, it says use a problem-solving strategy. In this section, we go over just what that strategy is, and then just some kind of generic examples of different kinds of problems. In section 3.2, the focus is on percent problems, problems involving like taxes and percentage discounts and other types of percent problems, percent increase and decrease, and others. And section 3.3 will be about mixture applications. That's problems where you have a combination or mixture of a couple of things, and there's some sort of weighting going on that affects how much of each quantity you have. For example, a typical problem there is a jar of coins. Let's say that you have a jar of coins that is all quarters and dimes, and you know how much it's worth. Let's say it's worth $45.20 or something, and you want to know how many quarters you have. If you know how many coins there are altogether and how much dollar amount there is altogether, then you can figure out how many coins there are. That would be a typical example. We'll, of course, see more when the time comes. In section 3.4, the focus is on geometric stuff, problems involving rectangles and triangles, and the Pythagorean theorem, which may or may not be familiar to you. And if not, that's okay, it will be after this. Section 3.5 is on uniform motion questions. In there, what's uniform is that the things that are the objects in the problem are neither speeding up nor slowing down. There's no acceleration in section 3.5, but it can involve either two planes, boats, trains, cars, or people, or whatever, doing one thing, maybe approaching each other, going away from each other, maybe going in the same direction at 2 different speeds. Maybe they're going towards each other. You might want to know how long it takes them to reach each other or pass each other, or if they're going away from each other, how long it will take them to get a certain distance apart, and so on. In section 3.6, it'll be applications involving linear inequalities, and a lot of that will be similar to what we do in section 3.1, only instead of saying that 2 quantities are equal to each other, it'll just say that 2 quantities are at least or at most some other quantity. Okay, so that's basically it. Story problems, in short. The first section, though, focuses on the strategy to solve most story problems. So the first step, of course, is to read the problem. You're in all likelihood going to need to read the problem more than once. Math, as you know, is a very kind of detail-heavy subject. You can't just kind of skim it like People magazine or a website or something and get the idea of what's said. Often one word can make all the difference. So you really need to read it word for word and carefully. And often you may need to read it more than once. Be careful that you're reading it more than once doesn't make you feel like dumb or anything, because you're not dumb. It just means you need to read it more than once, okay? So don't necessarily just read through the problem once and then jump right in. Okay, make sure you understand the problem and make sure that you understand any new words. For example, in some of the problems we'll be doing in a few minutes, we'll be working on consecutive integers. So we need to make sure we know what consecutive is and what integers are. If the problem is about a perimeter of a rectangle, we need to know what perimeter means, and so on. Make sure you understand any new words. And 2, decide what quantity you are looking for. So if the problem is about that jar of pennies or dimes and quarters that I was mentioning earlier, maybe you're looking for how many quarters there are in the jar, or maybe you're looking for how many dimes there are in the jar. Okay, whatever it is that the problem is asking you to find, let that be your variable. 99% of the time, you want your variable to be whatever the problem says, find whatever. Okay, the length of the rectangle, or whatever it is the problem is telling you to find, you almost always want to make that the variable. Okay, choose a variable to represent that quantity. Often, I didn't put it here in writing, but usually you want to make the variable meaningful, we use X a lot in algebra, but if it's you may want to use D for dimes or Q for quarters or W for the width of the rectangle if it helps you understand the problem and get through it better. Okay. Whenever possible, write the other quantities in the problem in terms of that variable. So for example, let's say that we had that jar of coins and we know that there are 80 coins total. And you know that, or you've decided that N, let's go with D for a number of dimes. Okay, if there are going to be D dimes in the jar and 80 coins total, then if we want an expression for the number of quarters, we don't have to use another variable, right? The number of quarters would be 80 minus D. That is the rest of the coins. Okay, so we'd have an expression for both dimes and also the other quantity in the question, which was the quarters. And then the other quantities in the question might be 0.10 times D. That is going to be the value of the dimes. Remember that the number of coins is not equal to their value, right? So 10 dimes is worth $1, and that's 10 coins. 10 coins is $1 there. Okay, 0.25 times 80 minus D will be the value of the quarters. So this was the value of dimes, and this was the value of the quarters. All of this is about putting the other quantities in the problem in terms of the one variable you picked. Notice that I used N for all of, or D for all of that for dimes. We didn't have to introduce another variable Q for quarters. Okay. Step 4, usually the hardest part probably is step 4. Translate the story into an equation. Typically you want to think, well, if it's an equation, two things are equal to each other. What has to be equal to what? Okay, is the distance traveled by the train equal to the distance traveled by the boat? Okay, then set those two distances equal to each other. Okay, figure out what two things are equal. You may want to draw a picture. You want to make a table that shows all the different quantities to each other. If, like I said, if the problem is about a rectangle and it's the relation between its length and width, you might want to draw a rectangle and then label it. Okay, then step 5, use algebra to solve the equation. Okay, carefully, as we've studied, use algebra to solve the equation. And then finally, check your answer to make sure that it makes sense. Mistakes happen. I make a lot of mistakes. Make sure that check your work. Make sure that it sounds reasonable. Sometimes we make mistakes in algebra. Just the calculations. You add 5 on one side, but you've added 6 on the other side, right? Or maybe an error in the conception of your problem. Maybe you misunderstood the problem, or you answered a question that wasn't asked. A lot of times in word problems, what's nice is that because it is a word problem, you have a sense of what makes sense. An example from trigonometry, which of course isn't this class, but let's say that we have a ladder that is 12 feet long, and it leans against the house, and it makes, let's just say, a 40-degree angle with respect to the house. It doesn't matter. And like I said, this isn't a trig course, and so you don't really need to know how to do this. But you've been around on the planet long enough to know that if I asked you, okay, how high up the house will the ladder reach? I go through all my calculations. If I came out with 20 feet, would that make sense with a 12-foot ladder? Hopefully you're sitting there saying, no, you couldn't reach 20 feet up a house with a 12-foot ladder. Okay, so that's what I mean when I say, okay, well, it has to make sense. The situation, physical situation has to make sense. Going back to our jar of dimes and quarters, we should have a whole number of dimes, right? We're not going to have 33.287 dimes, right? Or a negative number of dimes. Okay, check your answer to make sure that it makes sense. Okay, so that's it for the strategy. Let's give it a try. We've got a few here. Let's start at the top. Okay, so here it says George bought a bookshelf on sale for $120, which was 2/3 of the original price. What was the original price? So looking at the end, that's where we're asked to find what we're trying to find. In math, unlike English, English has for a paragraph a topic sentence at the beginning. Often in math, what we're asked to find is at the end. So looking at the end, we want to know the original price. I'm going to let X stand for the original price. Okay. And then that's what we're trying to find. And then it says George bought a bookshelf on sale for $120. That was 2/3 of the original price. So this problem has only 2 sentences in it. The last sentence is just telling us what to look for. The first sentence then has to have all the information in it that we need. He bought a bookshelf on sale for $120. That was 2/3 of the original price. So this $120, we have to relate that to the original price. The was here, past tense of is, that's telling me where the equal sign is going to go. The 120 is or was 2/3 of the original price. Of means multiply. We have 2/3 of the original price, and that's equal to the 120. Okay, so then that's our equation. Let's solve that. We're going to multiply both sides by 2/3. That's wrong. Let me go ahead and finish it, okay? It's wrong, though. So paying attention and you're worried. That's wrong. I know it's wrong. Okay, so 3 goes into 120, or 2/3 of 120 is 80. X. Okay, I'm all done. Let's say. Let's just pretend I'm all done right now. Okay, so now the common sense part. We're just checking. Okay, so he bought this thing on sale for $120, and we want to know the regular price. If he bought it on sale for $120, the regular price should have been more, right? So me coming up with 80, I'm messed up, right? So the regular price has to be more than whatever he's buying it on sale for. And so looking back, what I did wrong is instead of multiplying by 2/3, I should have multiplied by 3/2. So in this case, it wasn't so much a conceptual error in implementing the solution. It was more just an algebra error than anything. Okay, so now we're multiplying both sides by 3/2. So then our right side will just be X, and then our left side will be 180. Okay, so we could say it was $180. And that sounds reasonable, right? Okay. All right, this one, there's no real story for it. It's just numbers. Here it says the difference of a number and 8 is 17. Find the number. So let's go with n's number. There's again only 2 sentences. The second one is telling us what to do. And the first one has to have everything we need in it then. Difference sounds like subtraction. The difference of a number and 8 is, that's the equals 17. So there's our equation to solve. It looks like n is 25. The number is 25. It's a good idea to get into the habit of writing out your answer as a sentence. A lot of teachers like that instead of just giving 25, okay? All right, let's try one more. Bob bought textbooks and notebooks at the bookstore. The number of textbooks was 3 more than twice the number of notebooks. He bought 7 textbooks. How many notebooks did he buy? So taking a look, there's a lot there, right? So the last part is the actual question asking us how many notebooks he bought. So I'm going to let that be the variable. I'm going to go with n as the number of notebooks. That's what we're trying to find. With this, it can be kind of easy to get kind of lost in all the wording here too. Because if you take a look at it, it's all this notebooks, textbooks, notebooks. It's easy to get kind of lost in all that. So we'll just kind of go through it real carefully, okay? He bought textbooks and notebooks at the bookstore. Okay, so that's kind of the background information in first sentence. The number of textbooks, so there's another quantity in here, is how many textbooks he bought. And it says it was 3 more than twice the number of notebooks. So we need an expression for the number of textbooks. And the yellow highlighted part here is going to give that to us. So the number of textbooks is 3 more than, so 3 plus 2 times the number of notebooks. Okay, so that's that. We now have an expression for how many notebooks there are, that's n, and how many textbooks there are, 3 plus 2n. And then finally, it says he bought 7 textbooks. So that tells us that the number of textbooks is 7, right? So this sentence, in kind of green, blue, says that he bought 7 textbooks. So then this quantity 3 plus 2n, which was our number of textbooks, has to be 7. There's our equation. The expression about the number of textbooks is 7. And so from there, we can figure out the number of notebooks. Subtracting 3, we'll get 4, and it's 2. He bought 2 notebooks. Okay. All right, that will do it. Makes sense to me. Okay, another number problem. Here it says one number is 6 more than another. The sum of the numbers is 24. Find the numbers. This problem has 3 sentences in it. The last sentence, find the numbers, is just telling us what to do. This time we're finding 2 numbers is all. The first sentence tells us how the first number, called one number, is related to another. The next one tells us something about the sum of the numbers. So there's a total of 3 sentences. The quantities in here look like what's being referred to as one number. I'm going to let x be one number. Okay, and then the other one is called another number. But in this, we want to avoid using another variable, like y for another number, because in the first sentence, it's telling us that one number is 6 more than another. So if one number, let me temporarily use a for another. Okay, one number is 6 more than another, then that tells us the another number has to be 6 less than the one number. Okay, so I can re-express the another number as x minus 6, or 6 less than the one number. So this gives us an expression for both the one number and the another number. Next, it says the sum of the numbers. So here's an example where we need to make sure we understand the words. Sum means addition, right? So that means we are adding the 2 numbers, the one number and the another number, and it has to total 24. That will give us 2x minus 6 equals 24. 2x is 30, so that x is 15. So now the algebra has given us the one number. The another number is 6 less than that, and so is 9. So the numbers are 15 and 9. Okay, in this one, you probably noticed that it felt a little awkward how I had to introduce this kind of other variable a temporarily in order to get this done. The reason for that is that in the first sentence, the one number is described in terms of the another number. So maybe it would have made sense to let the variable be the another number. So I'm going to go ahead and rework this problem with the variable being another. So this time, just so it's not maybe as confusing, I'm going to use n for the variable, and I'm going to make that another number. Okay, so the n here is standing for another number. And then we're told that the one number is 6 more than another. So 6 plus n is what the problem is calling one number. Okay, and then it says the sum of the 2 numbers, the another number and the one number, is 24. So 2n plus 6 is 24. So 2n is 18, n is 9. Okay, so I haven't done this wrong. We've just found the smaller of the two numbers first, the another number. Remember that the one number is 6 more than that, so 6 plus 9 would give you the 15. So we would still get 9 and 15 as the two solutions of this. So the work here looks different. I think the second way looks a little better. It's a little easier to understand, but either way is okay. You want to be kind of careful about how you pick out the variable because it can determine or dictate how easy or how hard the problem is. Okay. All right, so next up, another sum problem, but this time it's the sum of two consecutive integers. So consecutive integers means that they come one right after the other. And integers are just numbers that are either whole numbers or negatives. There's no decimals or fractions or anything in here. Okay, so find the numbers. So I'm going to let n be the smaller one. Okay, that's an arbitrary choice. We could have let it be the bigger one. Okay, there's two numbers. They're consecutive. If n is the smaller one, n plus 1 is the larger one. So then their sum, that means n plus 1 has to be 95. So 2n is 94. And so then n is what, 47? So they're 47 and 48. Okay, and I knew that because the n, I told us at the beginning, was the smaller one. If you chose n to be the larger one, it's going to be different looking work, but the same ultimate answers. Okay, so for the next one, we want to find 3 consecutive integers whose sum is negative 96. So take a minute, pause the video, and try it yourself and see how you did. Okay, so let's try. I'm going to go with x as the smallest one. Okay, so if x is the smallest, x plus 1 has to be the middle number, and then x plus 2 has to be the biggest number, right? If they're consecutive, they're one after the other. So if you know the smallest, then you know the next one and the biggest one. If we had let the variable be either the middle or the largest, we're going to have different looking work, but again, we'll have the same answer. So once again, the sum of x plus 1, and x plus 2, there's my 3 numbers. I'm going to wrap these in parentheses just to maybe help it be easier to read, but that wasn't necessary here because they're all additions, right? The sum there is negative 96, excuse me. We'll have 3x plus 3 is negative 96. So 3x is negative 99, and x is negative 33. Okay, so that means that's the smallest one, right? Negative 33, negative 32, and negative 31 are our 3 numbers. Okay, once again, you'll notice that even though we're finding more than one thing, we're only using one variable. If we tried to use x, y, and z here, then I think we're working ourselves a little too hard. Okay. Okay, let's try this one next. So here, Tom and Lily together earn $110,000 a year. Lily earns $16,000 less than twice what Tom earns. How much does Tom earn? So take a minute, pause the video, try to set up and solve this one, and then restart the video and see how you did. Okay, so here, there's 2 sentences in the problem. The first one has all the information in it, and the second one is just asking us how much Tom earns. Okay, so let's let that be the variable this time. I'm going to go with T for the amount Tom earns. Capitalize that. Okay, that's what we're trying to find. Okay, and then here it says Tom and Lily together earn 110. I'm missing a 0 there. So 110,000 a year. Okay, Lily earns 16,000 less than twice what Tom earns. So for Lily, it's going to be twice Tom but 16,000 less. Okay, Lily makes 16,000 less than twice what Tom earns. Okay, together they make 110,000. Together, or adding together the money they make. So that's going to be Lily's amount plus Tom's amount, and together that makes the 110,000. Okay, so then that's the setup. So then we'll solve that. Let's combine like terms with the t's. We have 3t, and then that will equal 126,000. Okay, adding the 16 to both sides. And then for t, I need to divide, huh? We're going to have to divide the 126,000 by 3. Give me a minute to do that. Looks like 42,000 per Tom. So Tom makes 42,000. And then Lily makes the rest of it. To figure out how much Lily makes, you can either do this, you can do this in two ways. You could either use the formula we had right here, that Lily is 2t minus 16,000, or since you know that the couple as a whole makes 110,000, you could subtract Tom's from that. So that's what I'll do. It sounds a little easier. Okay, so this is all in thousands. We have 110 minus 42, so that's going to be 67. That's 67,000. Okay, and then I guess I could check, right? I should check. 2 times Tom would be 84. 84 minus 16 is 68. So I'm off by a little bit. Okay, so my check has exposed an error in here somewhere. So let me find that. All right. So my error, as it turns out, is in subtracting the 110 minus 42 should have been 68. So that was where the problem is. So it works out that Lily makes the 68,000. Okay, that takes us to the end of that. The summary here is we had gone over basically a strategy for solving story problems along with some examples. The strategy as a whole kind of applies to basically most story problems. In the remainder of the sections, we'll be going through specific problems types. In the next section, we'll be looking at percent problems. In the meantime, let me know if you have any questions, and then have a great day.